All right, before we start, are there any questions about anything we talked about on Monday? Man, this week is almost gone.
I have a question.
Go ahead.
Did you assign any problems for us to do on our own on Monday?
From Monday, let me look back. Let's see. I think yeah, right here, I did. This question 164B.
Okay.
And we're gonna do, we did 166. I want you also to do 165 on your own, because this is very, very important to practice. You have to be able to, you have to practice. So that's the best way and the easiest way to get better is to practice. On my computer, slow down. Sure. Got it. Yeah. So I want you to practice on those problems on 165, converting the condensed form, because we did quite a few the other day, but you got to practice. And with just like with anything else, reps. If you ever play sports, you know that reps are all important. The more reps you do, the better you get. So I wanna keep pressing. Let me see where we stop. We stop with this example right here, I think. And I cleaned those notes up before I uploaded them to Blackboard, because it was kind of it didn't look so hot. All right, so let's do something, because I want to introduce you. We got about 3 other topics that we need to talk about. We need to talk about resonance. We need to talk about dipole, polar covalent bonds, and we also need to talk about functional groups. But the functional group part, I think I'm going to push that to the second exam, because it's just so many functional groups. But definitely we're going to talk about resonance and dipole moments, and we're going to like kind of bring that in today, and we're going to start talking about dipole. I sent the dipole video too. Hopefully you had a chance to watch it. We're going to go use that to go through the rest of this handout. All right. Are there any questions about any of the topics that we've covered so far? So let me hopefully I'm not making y'all dizzy going back and forth with this screen. All right, so today, all right, resonance, we're going to squeeze in some resonance, and then we'll talk about polar covalent bonds. All right. So, and let's take an example, and we also are going to talk about, let me see what else is on this sheet. Yeah, we won't touch the functional groups yet. We'll do that later. But we're going to talk about, so this is kind of bleeding over into 1A, because 1 and 1A, you know, they both of the topics are very similar, and they all build on each other. So we're going to talk about solubility, and physical properties. Right. So even if we don't get a chance to talk about functional groups, for this first exam, it'll be on the second exam. And again, I'm thinking that we'll move the exam at least to next Wednesday instead of Friday. And the way it's going to work, we'll still have class on Wednesday. We'll still go through like the whatever 50 minutes in class or whatever, and then you'll have between Wednesday and Friday to take the exam. So I'll leave it open from Wednesday, Thursday. It'll close like Friday night at like 11:59, something like that. But I'll put an announcement out so you'll have all the information you need. Right. So I wanna jump in talking about. Was there a question? Yes, I want to jump in and talk about resonance. Now, I actually want to do it using this example right here. So I'm gonna cut that out. That's a great place to start. And it gives us
Could you scroll back up real quick?
yeah, here we go.
Did it say for 1.65 that it was on our own? That whole
Yeah, you need to practice converting those
Okay.
condensed forms into line and scalable forms.
Okay. Awesome.
And let me give you the ones to do, because that's a lot of problems. So I'm not gonna do A until we talk about functional groups. We'll do B, C, and B, C, and all of these are different. All of these are different functional groups. Yeah, I'll just for now, B and C will be fine under that, because the rest of those are other functional groups, and I don't want to open that can of worms and shit. All right, and so let's talk about resonance. But before we talk about resonance, I want to talk about I want to actually touch that second topic first, because resonance is all about sharing electrons. So I want to talk about the second section first, the polar covalent bonds. Right, so we talked about like bonds between atoms already, and we talked about like the different types of bonds. We talked about covalent bonds, and somebody help me with the definition of what is a covalent bond? What does the covalent mean? What does that mean? Anybody?
They share electrons.
Shared electrons. Right? And so normally when we think about a covalent bond, let's just think about a carbon sigma bond, where you have an electron here, you have an electron here. Sorry about that. A carbon. Right? You got an electron here. And then these two things come together and overlap. Remember, we talked about that valence bond theory, where two valence shells come close enough to overlap and share electrons. And so now you get a bond between the two carbons, right? Where the two lobes overlap with the electrons. And so those electrons are between the two carbons and they're evenly distributed. Right, so evenly shared. Let me say shared, not distributed. This would be an example of what we call a non-polar covalent bond, right? Where the electrons are evenly or equally shared between the two atoms. Right, non-polar covalent. So you have two atoms, you have a bond between them, and the pair of electrons between them are equally shared. Now, if you have a bond between two atoms, but the electronegativity between the two atoms is like huge, the difference in electronegativity, let's say between carbon and fluorine, right? Fluorine has an electronegativity of 4.0. Carbon has an electronegativity of 2.5. So the difference in electronegativity is 1.5. That's big, that's huge. So in this case, if I were to show you the bond between those two, it's still a sigma bond, but the electrons are going to be more towards fluorine because it's more electronegative, right? So this is an example of what we call a polar covalent bond. So it's a bond between atoms of greatly different electronegativity. Right? Does everybody remember what what electronegativity is? Like what it's a measure of? Anybody?
Is electronegativity just like the willingness to accept electrons?
Yep. It's like the I like to call it in simplified terms like the love of an atom for electrons. So the higher the electronegativity, the more that atom loves electrons, right? The lower the electronegativity, it's the opposite. It doesn't really care, about the electrons. So highly electronegative atoms tend to polarize bonds, right? If you have a bond, a polar covalent bond, then that bond is polarized in the direction of the more electronegative atom. So I'm going to draw an arrow to here. This is called a dipole arrow. Di meaning two, pole in reference to the polarity. So anytime you have a polar covalent bond, it is going to polarize the bond. The atom, the more electronegative atom, is going to polarize the bond through what's called induction. So polar covalent bonds are polarized through what's called induction. Right, that's induction is the ability of an atom to polarize a bond. Right, so a highly electronegative atom is going to induce polarity. It's going to generate polarity. What that means for the atoms is simple, right? What's the charge on an electron? Anybody remember that from part 2 or part 1 of general chemistry?
Do you mean like it being negative?
It's negative. So if I pull electrons away from an atom, what do you think is going to happen to the charge on that atom? Is it going to become more positive or more negative?
if you pull it away, or
Yes, if you pull it away from it,
it become more positive?
more positive. So when you have a great, when you have a polarized bond, the atom in that bond, the atom that's less electronegative is going to become, wrong button, is going to become partially positive. That's a lowercase Greek delta. It's partially positive. And then the atom that's more electronegative is going to become partially negative. The direction of the dipole is telling you where the electrons are going. So if the arrow is pointing towards fluorine, that means that fluorine is going to be pulling electrons towards itself, and in the process becoming more negative, and it's pulling electrons away from carbon, which is in the process making carbon more positive. This is a very important concept for when we start talking about reactions and where reactions happen within a molecule. Normally, they're going to happen at some polarized site, or some site that has the potential to become polarized. Right? So how do you tell if a bond is polar covalent? Right? There's a way. Normally is if the difference in electronegativity is from 0 to 0.3, then it's nonpolar. And this changes actually depending on what book you use. Some books have a higher scale where the polar covalent bond ends at a higher number. I'm going to say for us, from 0.4 to 1.5, we're going to say would be considered polar covalent. So if the difference in electronegativity is 0.4 to 1.5, then we'll say it's polar covalent. Anything greater than 1.5, or I'll say 1.6. is bordering on being an ionic attraction. All right, we okay so far? So if I have a bond like a CF bond, the difference in electronegativity is 1.5. And so that means that bond is a polar covalent bond. All right, any questions about that? All right, let's keep moving. Because sometimes if you have a molecule that has a polar covalent bonds or multiple polar covalent bonds, then you generate in that molecule what's called a dipole. All right, let me put another page in here real quick. Right, so you have if you can have a dipole, an individual dipole, but that doesn't always necessarily translate to a molecular dipole. So if you have a molecule where you can actually see the flow of electrons and they're flowing in one direction, creating like overall polarity, then we call that a dipole moment. I like to call it a molecular dipole. Right? So let's take, for instance, a molecule like acetone. All right, this will give me a chance to talk about something else too. Just thought about that, so that's good. So let's take acetone for instance. And functional group wise, this is a ketone. I know we haven't done functional groups like officially yet, but I like to introduce stuff when I see it because it gives you kind of a preparation for when we actually start talking about functional groups in detail. Right? So this is acetone. Let's think about the carbon-oxygen bond, right? That carbon-oxygen double bond. Do you think that's polarized? Is that polar covalent? Is it non-polar covalent? Is it ionic? How would we know?
You have to know the electronegativity of each atom.
Yes, you need to know the electronegativity of each atom so you can determine whether or not the bond is polar covalent or non-polar covalent. So oxygen is 3.5. It's the second most electronegative atom on the periodic table. And then carbon is 2.5. So the difference in electronegativity here is 1. It's actually a very polarized bond. Right? Because we said our scale 0 to 0.3 is non-polar, 0.4 to 1.5 polar, and then 1.6 is ionic. So this has a difference in electronegativity of 1. So there's a gigantic dipole going this way towards oxygen. All right. Any questions about that?
So would we have to memorize the electronegativity of all the atoms?
No, you'll be given the electronegativity. You just need to know how to find the difference, right? I'll give you on the exam, I'll give you a periodic table with the electronegativity differences. Well, the electronegativity values. You just need to calculate the difference. Now, if you had asked me that question in 1980, I probably would say, yeah, memorize them. But it helps to memorize certain ones because you see those atoms a lot over and over again, like fluorine, oxygen, carbon, nitrogen, some of the halogens. But it's up to you if you want to undertake that, but I'll give you the values. You just have to calculate the difference. All right. Now let's think about something else. Do you think that carbon bond is polarized?
No.
No? You sure about that?
Don't they have the same electronegativity?
They do. But there's a catch here. And if you watched the video on hybridization, was it on hybridization or was it on skeleton and line forms? I can't remember. It was one of those videos. What's the hybridization state of the central carbon that's bonded to oxygen?
2.5.
SP what?
2.
SP2. And these over here, SP3. Did anybody catch this it was at the tail end of one of those videos talking about how hybridization state and electronegativity are connected? Anybody?
Yes, it depends on how many S's there are.
Ooh, who is that?
Sanaya.
Put your cash app in the chat. Tell me more about that. I'm buying you lunch today. Tell me more about what you mean by that.
As the I think it's as the S increases, I think the percentage, I forget what the percentage is for each hybridization, but
Yep.
yeah.
It's S character, right? Is that what you're getting at? The percent S character?
Yes.
Man, I gotta get me a stylus or something because my finger is really sticking to this screen. Percent S character. So SP3 is 25% S. Is that right? You got 4 total orbitals and only one of them is an S, so it's 25%. Yes or no?
I would think so.
Yes.
Yeah, it's four, there are four things, they gotta add up to 100. So if you take one out of the four, it's 25%. If it's SP2, that's 30, would be 33 point something cents, repeating decimal, right? 33.33333, whatever. But we'll just say 33% S. And then SP is 50% S. Right? The more S you have, so the higher the S character, the higher the electronegativity of the atom. Hopefully you can understand my shorthand down here. So the higher the S character, the higher the electronegativity. Are y'all following? Yes, no, maybe, somewhat,
Yes.
right? Higher the S character, higher the electronegativity. So what does it mean if an atom is more electronegative again? What does it mean about that atom in reference to electrons? Does it love electrons more or less?
Loves them more.
Loves them more. So if you have an sp2 carbon bonded to an sp3 carbon, which one of those carbons is gonna love electrons a little more? The sp2 or the sp3? Look at, I purposely zoomed out so you can see the chart. Which one has more S character? sp2 or sp3?
SP2.
sp2. So that bond between the carbons at, face value, it doesn't look like much, but if you know what's happening on the atomic level, then you know that that bond is a little bit polarized, slightly polarized towards that central carbon. Following? Because of that difference in hybridization state. Yes? No?
Yes.
Speak up if it's not clicking.
It's not clicking.
Okay, what's not clicking? Which part?
The character.
The S character?
Yeah.
All right, let me put it in terms of let me do this. Don't take this the wrong way. Don't be offended. I'm just trying to make it make sense. Right? I got four, let's say 4 balls, right? How many of them are blue?
One.
1. So what percentage of those balls, of those 4 balls will be blue?
1%.
1 out of 4?
Yeah.
25%, right?
Yeah.
All right. So let's say if I have 3 balls and one of them is blue. What is that? What percentage?
2 out of 3. Well, you
Blue,
said
not
three
red.
balls, right?
Blue.
Oh, 1.
1 out of 3.
1 out of 3.
Right? Be 33%. Is that right?
Yeah.
If I have 2 balls and one is blue and one is red, what percentage of that is blue?
1 out of 2.
1 out of 2, or 50%. Is that right?
Yeah.
So over here, when I make my hybrids, if I got 4 things, S, and then let me try to keep the same vibe. Right, that's what sp3 is, right? It's mixing S and 3 Ps. Is that right?
Yeah.
So what percentage of that mixture is S? I should have did it the other way around. Hold up. Let me do that. Because I want to connect it with the example I just used. What percentage of that is S? If I'm looking at all 4.
1 out of 4.
1 out of 4, which is what? 25%. Is that right?
Yes.
And then down here, it's the same idea. What percentage of that will be S?
1 out of 3.
1 out of 3, 33%. Down here, same thing. Uh-oh, I'm too far away from the SP, my bad. Is that right? S&P 50%?
Yes.
So when I say something is SP2 hybridized, I'm saying it's 33% S. If it's SP3, it's 25% S. But the overarching idea is that as I decrease or increase the amount of S, I'm also increasing the electronegativity of the atom at the same time. Because what's happening is the orbitals themselves are getting smaller and tighter. And so the electrons are being held more closely to the nucleus. So when I overlap that with something, that nucleus, which is positive, is going to be more exposed and it's going to pull on the electrons in the other atom more. So a sp2 carbon bonded to a sp3 carbon is going to have a slight dipole towards the sp2 carbon because of the percentage and because of the electronegativity difference that results from that percentage. Did that clarify it a little bit?
Yes.
Okay, great. All right. So
I have a
go
I
ahead.
have a quick
Yeah, go ahead.
question. Okay, so I understand how like the SP2 and all that has a higher electronegativity because of S character. I get that.
Mhm.
But the way the arrows are pointing, so it's pointing towards the carbon, the SP2,
Yes.
that had a higher electronegativity.
Yes.
And then whenever I was trying to figure that out, I noticed though, like if you go the carbon to the oxygen, the oxygen had a higher electronegativity. Arrow was pointing towards the oxygen.
Yes.
Can you like, I guess I'm just kind of, I was looking towards which one's bigger and smaller and like going that way. How is it that we figure out which way the arrow goes?
Great question. So what I'm trying to do is show the atomic dipoles first and use those to help us understand the molecular dipole, that the whole molecule has polarity to it, right? And so what we have to think about these dipoles, they're actually measurable. Like there's actually an instrument called a dipole meter that you can measure dipoles of certain solvents, certain molecules and things like that. But if you notice, these are vectors, right? That dipole arrow is indicative of a vector because not only do you have magnitude, but you also have direction, right? The dipole has a magnitude, right? It can be a huge dipole or it can be a weak dipole. And it has a direction because of the flow of electrons. So when I take those vectors and add them up, you can see that they're all going in the same general direction, which is this way. Is that right?
Yeah, I see what you're saying now.
Yeah, so what I'm doing in determining the molecular dipole is I'm summing up the atomic dipoles and seeing if they all have a general direction of electron flow.
Okay.
Right. So what that means, go ahead, Tia.
You can go ahead.
You sure?
Well, okay, so you just said you got the sum of all of the atomic dipoles.
Yes.
How do you do that?
Well, we're not really summing them up numerically. We're just looking at the vectors and saying, oh, because you can add vectors together, right?
Right.
If they're going the same direction, you can sum them up and the magnitude is going to increase. If they're going opposite directions, then they're going to cancel each other out. Is that right?
Right.
Right. So what I'm saying is the vectors have a general direction that they're going. And so I could say that this molecule itself has a dipole, and you can look up the dipole for acetone and you'll see it's a pretty good size number. It's a very polar molecule. And that's important because polarity is a physical property and it kind of dictates other things about the molecule, like the boiling point, what dissolves in it, what won't dissolve in it, that type of stuff.
So I have another question.
Yeah, go ahead.
So did you determine the molecular dipole from the dipole between oxygen and carbon? Is that?
It's all of them and the carbon-carbon dipoles. Because remember, if the sp2 carbon is a little more electronegative, that's going to create a little dipole between those carbons too. So there's really like a summation of the dipole vectors. That's how I get the overall dipole.
Okay.
Mm-hmm. All right, now with the overall dipole, what can we say about the end where the arrow is? What is the general, what does that arrow mean? That means that electrons are flowing that way, am I right?
Yes.
So I could say that this end of the molecule is going to be partially negative, and then this end will be partially positive. And when we start talking about intermolecular forces, which will be next, and we kind of layer in the functional group stuff in there, because it's the functional groups that give the molecules their intermolecular properties, like dipoles and things like that. So I'm gonna layer those two things in together. All right. So you can see how a dipole creates this polarization, right, in this molecule. So sometimes you have molecules like acetone that have dipole. Sometimes you have a molecule like an alkyl halide, which we'll say C. Right, fluoromethane. Let's look at that. Now there's a big dipole between carbon and fluorine, right? We already said that earlier here. And then between hydrogen and carbon, that's not really a polarized bond, but the carbon is slightly more electronegative than hydrogen. So you're going to have some kind of like micro dipoles here, all going towards the carbon, right? And if that's the case, then can we say that this molecule has a overall dipole if all of your vectors are kind of going in the same direction?
Yes.
Yeah, we can say that. It's got a overall dipole. Let me change the color. It has an overall dipole because of the sum of those vectors are all, well, the vectors have a direction that go like all the vectors are moving in the same direction or the same general direction, right? All right, let's do another one because there are also some cases where a dipole is not possible. I'm gonna give you two examples of that. One is carbon monoxide, right? What we know about carbon monoxide, this carbon is sp2, so it's going to be linear. I'm not saying anything about the hybridization state in reference to its electronegativity, but just the fact that it's linear, right? And we know we have a dipole going here towards oxygen, and then here, right, towards oxygen. So those vectors are moving in opposite directions. Am I right?
Yes.
Yes.
All right, go ahead. I see two hands up.
Why is the carbon sp2? I mean, I only see two groups.
That's why it's sp2. It has two groups and it has two groups around it. That's the first way we recognize it. But the other way is that it has two pi bonds to it. Remember, this is the same as if this carbon was in a triple bond. We'll just put an H back here, right? Doesn't that carbon have two groups?
Yes.
And it also has two pi bonds to it?
Yes.
Because the triple bond is one sigma and two pi's. So it's the same thing, it's just configured a different way. All right, did that answer your question?
Yes.
Okay, great. Right, so it's sp2 is linear, but look at the dipoles. They're both going opposite directions, yes?
Yeah.
What do you think that means for the overall dipole?
Mm,
Cancel.
It cancels out.
They're going to cancel, right? So they're going opposite direction. That means they're going to cancel each other out. Sorry, can't spell. So for that molecule, there's no dipole. Right? No molecular dipole or no overall dipole because the dipoles cancel each other. Right? Another example would be something like difluoromethane. Let me show you that. I'm gonna write it out in Lewis form. Something like this, right? What do you think about that? Is that the same scenario where the dipoles are going to cancel each other? And let me do this because I'm going to show you something real quick and then why that particular structure wouldn't necessarily be possible. All right. So if I draw it this way, I can see that the fluorines are opposite to one another or anti, and that the dipoles are going to cancel, right? So no. You have atomic dipoles between carbon and fluorine, but the molecular dipole doesn't exist because the two fluorines cancel each other out. Now,
Question.
go ahead.
What about the dipoles between carbon and hydrogen?
Those are not strong enough to create a dipole and make this polar, if that makes sense. Because the difference the difference in electronegativity is so small that it's only like a micro dipole towards carbon, but it's not enough to create a dipole to say this whole molecule is going to be polar.
Okay.
Yeah, great question. Now there's if you were to write this like this, then you might, you may use that to try and argue for a dipole, but this is not going to exist because right here between these fluorines, this space between them, those electron pairs on fluorine, do electrons repel each other or do they attract each other? See if you remember that from part one.
Repel.
They repel.
They repel each other. And so those electron pairs are going to repel each other, right? And that's going to create instability in that if this is the structure for difluoromethane. So this is the preferred structure right here, right? Where there's minimal electron pair repulsion between those fluorines. Because if you wrote it like that, then, you could make the argument that, well, since both fluorines are on the same side, then maybe there's a dipole because the electrons are flowing in a similar direction. But the fact that the electrons repel each other, that structure probably doesn't exist. Or if it does, it exists in a very small percentage compared to this one. All right. So we're going to stop here. We're probably going to go ahead and move the exam to Wednesday because I still want to introduce you to, we want to work through some of these dipole questions first of all, and then, sorry about that. And we also want to talk about solubility, which is in the next handout, and functional groups and resonance. So we're going to move the exam to Wednesday. And the functional group, again, the functional group stuff may not be on that first test, but definitely we want to cover resonance. And I think dipoles and resonance kind of go hand in hand because dipoles and covalent bonds and orbital overlap, all that deals with the sharing of electrons. And that's exactly what resonance is. So when we come on Friday, we're going to talk about resonance. And then we're going to kind of park there because that's a big topic and it's a very important concept to understand. And then after that, we'll talk about the functional groups and intermolecular forces and all that stuff. So that may be on the second test, even though it's in 1A, part of 1A may be on the second test instead of on the first test, if that makes sense. But I want to touch the major topics, the hot topics first, and make sure we understand them, because everything else, and that's why I'm kind of spending so much time on these little topics, because everything builds on this. You understand the fundamentals, when we get to the next part, it's not as difficult. If any of this stuff is escaping you, you got to say something, because everything else in the class hinges on your understanding of dipoles, your understanding of polar covalent bonds, your understanding of structures and electron flow, which we're going to talk about with resonance and functional groups and all that stuff. Everything is going to hinge on that in part 1 and part 2. So please don't just blow this off like you don't need it. You're going to need it for the rest of the class, and you're going to need it for part 2. So with that being said, I'm going to stop recording, and then you can ask questions if you need to. Otherwise, we'll log out.